and another one towards theory reasoning, satisfiability modulo theories, and possibly beyond. So towards first-order logic, for example, there has been at least 2 generalizations to the Bernays-Schoenfinkel class, which is also known as effectively propositional reasoning, the PLLSX method by Ruzicka-Piskac and others, and the non-redundant close learning by Gabor Alagi and Christoph Weidenbach. And then there has been generalization to full first-order logic without equality for the time being. One is semantically guided goal-sensitive reasoning that I did together with David Plested, and the other one is conflict resolution by John Slani and Bruno Wolzenlogel-Paleo, and they also have an implementation called Scavenger that will be presented with Datimir Itegulov in the next keynote. Now, in this talk, however, we focus on the generalization of CDCL towards theory reasoning. So there has been a lot of work in generalizing CDCL to various fragments of arithmetic. For example, as early as 2009, there was a generalized DPLL by Ken Macmillan and others, or conflict resolution by Konstantin Korovin and others, natural domain SMT by Simon Cotton. Then Dejan Jovanovic and Leo Demura did first the cut into the chase method for linear integer arithmetic, and then the NLSAP method for nonlinear arithmetic. And this list ends in 2012, but I wouldn't be surprised if there were more. Now, all these procedures that I had in the previous slides, on the previous slide, are satisfiability procedure in the sense that they decide the satisfiability of a set of literals in the quantifier-free fragment of a theory T. They have 2 key features that are significant extensions, of course, in order to do theory reasoning with respect to the propositional paradigm represented by CDCL. One is that they allow assignments to first-order variables, not only to Boolean variables, and they allow explanation of conflicts by generation of lemma that contain new atoms. And this is also a significant departure from CDCL, because in propositional logic, all the lemmas are built by using atoms that appear in the input. Let's see an example in linear rational arithmetic. Suppose that we have those 3 constraints up there, minus 2x minus y smaller than 0, x plus y smaller than 0, and x smaller than minus 1. Say that the procedure decides to assign 0 to y. Then by the first constraint, we get x greater than 0, because if y is 0, the first constraint will give us x greater than 0. Which is in conflict, however, with the third constraint, which says x smaller than minus 1, okay? At this point, the procedure may explain this conflict by deducing minus 2 smaller than, minus y, sorry, smaller than minus 2, by what? By the linear combination of L0, the first constraint, and L2, the third constraint, the linear combination that eliminates x. So you see, we multiply L2 by 2, we take the sum, and we get minus y smaller than minus 2. Now, this atom, as you can see, is new in the sense that it does not appear in the input. And so this suggests that in order to do conflict-driven reasoning, which involves explanation of conflict in theories as opposed to propositional reasoning, it is necessary to infer new atoms. And note that this new atom does not only exclude the assignment y gets 0, which got us in conflict, but also all assignments of the form y gets c, where c is smaller or equal than 2. Now, the next step is to generalize this kind of mechanism from deciding the satisfiability of literals to deciding the satisfiability of arbitrary formulae in the quantifier-free fragment of the theory. Now, we may be tempted to do it by using the standard DPLLT framework, which is the classic for satisfiability modulo theories. But we cannot do it because this framework does not allow either first-order assignments or new atoms. So the answer to this problem, generalizing conflict-driven satisfiability procedures to arbitrary quantifier-free formulae, was given by the model constructing satisfiability system in brief, MCSAT, presented by Dejan Jovanovic and Leonardo De Mura in 2013.
A quick question.
Yes.
What does that mean, first order assignment? And sorry if it's a silly question.
No problem at all. A first order assignment is something like y gets to 0. It is first order because y is a first order variable. It's not a gets true or b gets false, which is all we have in propositional logic.
Right.
Feel free to interrupt with questions at any time, okay? So, MCSAT generalized this kind of theory, conflict-driven reasoning, to arbitrary quantifier-free formulae. Its main features are as follows. It really integrates the CDCL solver and the theory solver by viewing them as partners on the same level, as opposed to viewing the solver as the central engine and the theory solver as a satellite. It allows to have on the trail both Boolean assignments, such as L gets true, which of course can be shortened simply with L, and X gets 3. It works for any theory that is equipped with an inference system to explain theory conflicts. The inferences of this system are allowed to introduce new atoms. Because it allows the generation of new atoms, termination is non-trivial, and MCSAT ensures it by requiring that all the new atoms come from a finite basis. And in this manner, MCSAT lifts CDCL satisfiability modulo 1 theory. Now, MCSAT, the generic theory T in the MCSAT framework, has been instantiated to a few theories. Equality and linear rational arithmetic in the FMCAT paper by Dejan Jovanovic and others. Bit vectors in at least 2 papers, one at SAT 2016 by Alexander Zelic and others, and one at the Satisfiability Modulo Theory workshop this year, this month at CAV by Stefan Graham-Lengran and Dejan Jovanovic. And also equality and nonlinear arithmetic with mixed integer and real problems at VMK last January, again by Dejan Jovanovic. Now, however, this leaves us with several open questions. Problems from applications require combinations of theories, and this is well known. Now, how can we combine several conflict-driven satisfiability procedures? MCSAT is really a one-theory calculus. As a better way to put the questions, how can we combine multiple conflict-driven procedures, one of which is CDCL, since really already with MCSAT, the philosophy is to regard propositional logic as one of the theories. As another way to put it, how can we generalize MCSAT to generic combinations of theories, and which requirements should the theories and their procedures satisfy in order to ensure soundness, completeness, and termination of the combination? The new system CDSAT, which I present today, answers all these questions and show how can we do this. Now, the classical approach to theory combination is equality sharing, also known as the Nelson-Oppel method. Given a bunch of theories, each equipped with a satisfiability procedure, it gives a satisfiability procedure for the union of the theories. It requires that the theories be disjoint, which means that they can share sorts, equality, and uninterpreted constants, but they do not share predicate and function symbols other than equality. It handles mixed terms by separating them by introducing new constants. This is pretty standard. And the procedures need to agree on the shared constants and the cardinalities of the shared sorts. This is done in equality sharing in 2 ways. For the cardinality, it assumes that the theories are stably infinite, which means that every satisfiable quantifier-free formula has a model with domain on infinite cardinality. And for the equalities, it computes an arrangement which says which shared constants are equal and which are not. Now, the key feature of this method is that it minimizes the interaction between the satisfiability procedures, the interaction among satisfiability procedures being combined. And this is generally regarded as a plus, because these procedures only need to send around equalities or disjunctions of equalities between shared constants, and other than that, Each of them can work on its own, and they can be treated as black boxes. However, this leads to more open question, because when we have a conflict-driven procedure, then we observe that the conflict-driven behavior appear to be at odds with combination as black boxes. Indeed, for example, in the CDSAT paradigm, the conflict-driven satisfiability procedure for the theory needs to have full access to the trail on a par with the CDCL procedure for SAT. And they both compute, they both make assignments, they both compute propagations, they both work on solving conflicts. So the question is, can we generalize equality sharing to the case where the satisfiability procedures are conflict-driven? And can we then combine multiple conflict-driven satisfiability procedures with other satisfiability procedures that work as black boxes? And the new system CDSAT answers positively also these questions. So let's see what it is. CDSAT is a new method for theory combination. It generalizes conflict-driven reasoning to combinations of disjoint theories, so it has the same disjointness requirement as Nelson-Oppen. And it solves the problem of combining several conflict-driven procedures for theories T1, Tn to get one conflict-driven procedure for the combination of the theories. Also, CDSAT reduces to MCSAT as a special case when there are only two theories, one propositional logic with CDCL as a solver, and another theory T with a conflict-driven satisfiability procedure. Now, the basic features of CDSAT is that, first of all, it treats propositional logic and theory reasoning in a uniform manner. So formulae are seen as terms of sort prop, where prop comes from propositional, and it is a special sort that all the theories are required to have. Therefore, propositional logic is just one of the theories being combined. In this sense, it changes the standard SMT framework, where propositional logic is in some sense the sun, and all the other theories are like the planets going around it. Here, all the theories are on the same level, including propositional logic. With formulas seen merely as terms, what do inferences manipulate? The idea of CDSAT is that the basic data for inferences are assignments. And a key abstraction in CDSAT is to combine inference systems as opposed to procedures. Why is that? Because the idea is to combine multiple conflict-driven procedures. Now, every procedure has typically inference rules and some kind of control to apply the inference rules. When the reasoning procedures are conflict-driven, the control is the conflict-driven one. So this notion that we have seen at work in CDCL of guessing values, propagating consequences, and then when a conflict arises, explain the conflict and fix the model by backjumping based on what we have learned by explaining the conflict. Because this kind of control is in common to all the conflict-driven procedures, the idea of CDSAT is in some sense to open the black boxes, pull out the conflict-driven control, and centralize it in the central CDSAT engine, and therefore viewing the entities being combined merely as inference system, like they are stripped of the control. There are only the inference rules in the satellite being combined, and the conflict-driven control is central and unique for the entire engine. And we proved that CDSAT is sound, complete, and terminating. But how about black box procedures? We may have a theory for which we do not have a conflict-driven procedure. We have another satisfiability procedure which is not conflict-driven and that we would like to treat in the black box manner, which also has advantages because it minimizes the interaction. In the CDSAT philosophy, such a procedure is seen as an inference system, a theory module. In CDSAT, we call the inference system for the theories theory modules, with only one inference rule that merely invokes the black box satisfiability procedure, indeed as a black box, and uses it to determine that a bunch of assignments in that theory is unsatisfiable. And in this sense, CDSAT generalizes also equality sharing. because it reduces to equality sharing in case we only have procedures that are not conflict-driven. So if we have a bunch of theories for none of which we have a conflict-driven procedure, then CDSAT will simply reduce to equality sharing. Okay, let's see an example. Suppose that we have this set with F select store AIVJ equal W. So what are these? This is a combination in three theories: the theory of equality, the theory of linear rational arithmetic, and the theory of arrays. So F is an uninterpreted symbol. It comes from the theory of equality. Select is a symbol from the theory of arrays. It takes an array and an index and it returns the value. Store is another symbol from the theory of arrays. It takes an array, an index, and the value, and it returns the array where the value is stored at that position. And then the minus comes from linear rational arithmetic. The 2 comes from linear rational arithmetic. I and j are two indices, u and v are two values in the theory of arrays. If we look at the signatures of this example, we see that linear rational arithmetic will have sorts propositional in Q, where Q are the rational numbers. It has equality for each sort. 0 and 1 as rational numbers. Then there is the addition of the rational numbers, and there is the multiplication for every rational number, because this is linear arithmetic only. Arrays has prop, values, indices, arrays, equality, the two functions select and store. EUF has sorts prop, rational numbers, values, and equality on each sort, and the function f that goes from values to rational numbers. Why is this? Because if you go back to the example, you see that f, the uninterpreted function f, is applied to u, and u is equal to v, and v is a value, therefore u is also a value, and therefore f applies to values of arrays and returns rational numbers because it is equal to this expression which is in the rationals. Okay, now in CDSAT, everything is an assignment. So the initial state of the train will see the literals that we had in the set P, with each of them assigned true, the value true. And of course it can be abbreviated by simply omitting the assignment. And the idea is that the system works with one central public train which is shared by all the theories. So since everything is an assignment, we have assignment to propositional variables, assignments to first order variables, L gets true, X gets 3. But then we generalize further the notion of assignment. In MCSAT, you have only these two cases, either Booleans or first order variables. In CDSAT, we allow assignments to any first order terms. So we can also have an assignment to a select term, for example. And then we have assignments of truth values to atoms, literals, clauses, anything, because the formulae are seen as terms of sort prop. Of course, we can use the usual abbreviations, and flipping a Boolean assignment means going from L to its negation or vice versa. So formally, an assignment is a bunch of pairs where terms get values. Values have the same sort as the term they are assigned to. And in the assignment on the central train, we have assignments made by the different theories, because they all access the train. And therefore, we have mixed assignments with individual assignments coming from theory T1, theory T2, theory T3, and so on. Now, a point to be clarified, to be formal, to be proper, is that these numbers I'm using, for example, 3 or square root of 2, are not really symbols in the signature of the theory. So technically, we need what is called a theory extension, where we add new constant symbols to represent the values in the domains. This is actually standard practice in logic to build models. For example, we may add a constant for every rational number that we have if we are in arithmetic on the rationals. And we require these theories to be conservative, these extensions to be conservative, which means they do not change the problem. by definition, being conservative means that if a set in the extension is unsatisfiable, then it is unsatisfiable also in the original theory. So a set of formulae which is unsatisfiable in the extension is also unsatisfiable in the original theory. This means that if CDSAT works in the extension, when it finds unsatisfiable, it means the problem is unsatisfiable also without the extension. And on the other hand, if the original problem is satisfiable in the original theory, then there will be a model that CDSAT can build also in the extension, if you just take the contrapositive of this statement for satisfiability.
So, Maribel,
Yes.
how do you deal with theories that have uncountable models, standard models? Do you?
We do not. Here we are assuming that we can enumerate these individuals.
So, for instance, you can do nonlinear arithmetic then?
No, I mean, you only, the extensions are countable, so, you know, you don't have to bring in all the reals. You just have to bring the nameable ones.
How do
Oh,
you,
yes.
How do you maintain completeness?
So for these things, I mean, they just kind of, I mean, it's the same thing you do with symbolic reasoning. You're just doing it through.
Yeah, but there you allow yourself.
So you don't lose completeness because you still have the symbolic reasoning.
But you allow yourself to characterize solutions by equations as opposed to individual values, right?
Yeah.
So with the reals,
So
you could say,
in the nonlinear arithmetic, you bring in algebraic numbers.
Right, the algebraic reals are countable. This is what I was thinking earlier.
so you would do using algebraic numbers in this case as values.
Right, this is the case also for NSAT. The existing conflict-driven procedures I mentioned earlier for nonlinear arithmetic are for the algebraic reals, which are countable. Okay? Okay? Good.
So that means there's no just to summarize it, there's no full completeness for the reals, right? The actual reals.
Right, but
there
nobody
cannot
has
be,
it.
right?
I mean, we would not have. This is a method to combine satisfiability procedures. So
Right.
if someday one comes up with a satisfiability procedure for all the reals, then we would have the problem of combining. But for the time being, such a procedure does not exist,
Right.
because the procedures we have for nonlinear arithmetic are for the algebraic reals. This is true of
It's also
cylindrical
for all
algebraic
reals.
decomposition. This is true of NSAT.
Yeah, but there's no
I mean, I don't know
completeness
if
for all reals.
Yes.
There is.
No, this also
Yeah.
is just a complete
Yeah.
process. You just don't need
Yeah.
non-algebraic
Okay.
reals during
Okay.
the reasoning.
I'm confused.
So if there's a counterexample in the
complete.
reals, there's a counterexample in.
Okay.
Yes.
Okay.
And this is by first order logic.
Yeah.
So there's this Lemons-Cohen theorem that says that every theory has a countable model.
Yes, although you probably have to go meta to do
Yeah,
this.
but I mean, so accountability is not really an issue.
But
Yeah,
it's
no,
not
but you need to
related.
go meta if you
Yeah.
do this, you have
But
to
it's not
have a theory about the
related.
theory of the reals
I mean,
instead of the
it's
theory of
fine
the
to work with uncountable reals whatsoever. You just never need to reference these reals.
That's the same thing.
Yeah.
Yeah.
I mean, yeah, but this is, you know, a kind of operationalization. That is, when you give the constants, you're essentially giving all the facts you know about the constant. So, for example, what relationship it has, I mean, what relationship root 2 has to root 3 and so on. You're giving all of that.
Okay, maybe we should take this offline, but
Sure.
I'm still unclear about how you generate the constants.
Okay. Now I said that the theories all work on the shared central public trait. So we say that the sort is public if there are values for that sort that can be assigned publicly on the trait. So if the extension of theoretic K adds new constant of sort S, then this sort is public for that theory. And the meaning is that there are values of this sort that can appear on the right-hand side of an assignment in the central trait shared by all theories. Now, an assignment is plausible if it does not contain L gets true and L gets false, which obviously we don't want to have. So assignments are required to be plausible. that, a plausible assignment is allowed to contain something like T gets 3.1, U gets 5.4, T gets green, U gets yellow, where obviously the first two assignments are made by one theory and the second two are made by another theory. If this is the case, and if the whole thing turns out to be satisfiable, then when we build a model from this assignment, what happens is simply that the symbol 3.1 is identified with the symbol green in the interpretation, and the symbol 5.4 is identified with the symbol yellow in the interpretation. So it's only on the Boolean case that we require, of course, we don't want to collapse true and false. Now, the trail is central and shared by all theories, and all theories contribute to build it. Then every theory, we need to define the view that every theory has of this assignment, because of course every theory is concerned only with its own stuff, with what it can understand. So given an assignment, the view of this assignment H for a certain theory T contains the assignments in T, those made by the theory T itself, and it also contains equalities T equal S, where T and S are terms, if there are assignments that give to T and S the same value, for example 3, that's just an example, by another theory. And also T different from S if there are T gets 3 and S gets 4 by another theory. And this is of course for non-Boolean values, because for the Boolean we are not going to have repetitions like T gets true and T gets true again, or contradictions like T gets false and T gets true. That is forbidden by the definition of assignment. But for other sorts, we can have this kind of assignments, and therefore equalities and disequalities can be gleaned from the assignments of values by any theory in the view of this central assignment. For every theory,
Can you
yes.
get both T is true and T is green? Is that allowed?
Pardon me?
Can you get T assigned true and T assigned green? I mean, you're...
Yes, in principle we can get that, yes. And then we would have to see whether there can be a model where green is identified with true.
On that note, would you need to extend plausibility to any constants at all? I mean, can you assign x3 and also 4, for instance?
Oh, we are going to forbid that with another requirement that's coming next.
So that's different from plausibility. So
Yes.
Plausibility is about Boolean values.
Exactly.
Then you have another one.
Exactly, for first order values I have another notion. Thank you. So the theories are equipped with theory modules. So IK is the inference system for TK. And inferences transform assignments. As I said before, the basic data are assignments, not formulae. So for example, these are inferences that we could have in the theory of the reals, meaning the algebraic reals. If we have x get square root of 2 and y gets square root of 2, then it follows that x times y is equal to 1 plus 1 in other such examples. Now, how do we define inferences? Inferences are pair J inverse L, where J is an assignment and L is a singleton Boolean assignment. So inferences, by definition, only derive Boolean assignments. For example, getting y gets 2 from x gets 1 and x plus y gets 3 does not need an inference. It's not regarded in CDSAT as something that needs an inference. It is kind of basic evaluation of the variables, so we don't use an inference for that. Which means we do not require the assignment y gets 2 to be justified by an inference. It is only justified by the previous assignments to x and x plus y. Now, because all theories include equality, all theory modules include equality inferences that says if T and S gets the same value, then T is equal to S. If they get distinct values, then T is different from S. C and Q need to be distinct. And then reflexivity, symmetry, transitivity. Now, here comes acceptability, which is precisely the property that completes plausibility to keep into account also first-order assignments. So given an assignment for theory TK, which for example example could be the TK view of the train, an assignment that gives the value C to T. We use these Gothic letters to represent the new constants introduced by the extensions that are the values that we actually assign, is acceptable for the given assignment and the theory module for this theory if two conditions, 1 and 2, are satisfied. The first one simply says that J does not already assign a value to T. And this has two purposes. It prevents repetitions on all sorts, and it prevents contradiction on the Boolean sort. Because if we already have T gets false, we don't want to add T gets false again. If we already have T gets false, we don't want to add T gets true. And this is plausibility again. But then we have a number 2 requirement, which is specifically for non-Boolean assignment, and it is where acceptability extends plausibility. It does not happen, so this is acceptable if it does not happen that united with any subset of J, J prime subset of J, it allows us to infer some Boolean L. Remember that inferences only infer Boolean assignments, where the flip of L, the complement of L, is already in J. So that we would get a contradiction which is only one inference step away. So acceptability prevents this kind of assignment that causes a contradiction one inference step away. We also need...
That means in the previous example, where
Yes.
you had the x plus y is equal to 3 and
Yes.
yeah, so that means you would not have been able to assign y equals 1.
Exactly. Okay. Now, the last abstract notion we need, in addition to acceptability, is relevance, which says when a term is relevant. Because when we are looking at this central train where all the theories contribute, and the theory module wants to come up with a new assignment, we need to say that this assignment is for a relevant term, and what it means to be relevant. The term appears in the assignment. H is the general assignment we are dealing with. Now, appearing means appearing also as a subterm. So when we say that the term appears in an assignment, it doesn't necessarily mean that we have a pair T gets to C. We could also have FT gets something, and then T appears. So appears either as a left-hand side or as a subterm of a left-hand side. So it appears and has a public sort, that is the sort for which this theory has values to provide. Example, say that x contains square root of x gets square root of 5, fx gets square root of 2, fy gets square root of 3. X is of sort real, and it is relevant for the theory of the reals. Why? Because it appears in the assignment, and the sort of the reals is of course public for the theory of the reals, because that's precisely the theory which can assign real values to real variables. Otherwise, there's another way to be relevant, which pertains specifically to equalities. An equality T equal S, T and S are terms, is relevant for theory TK if the sides T and S appear in H, and their sort, the sort of T and S, is the sort of the theory, but it is not public in the theory. This is a little subtle, but let's see what it means. Take the same assignment as before. X gets square root of 5, fx gets square root of 2, fy gets square root of 3. The equality x equal y, where x and y both appear in the assignment, is relevant for the theory of equality by the second clause. Why? Because the sort of x and y, which is the real numbers, is a sort for a UF, we assume this is the case, and it is not public for a UF, because of course it is not a UF, it is not the theory of equality, which is responsible for assigning real values to real variables. That is the job of the theory of the reals. But the equality between the two reals that is relevant to the theory of equality, and that is why it enters in this definition. So again, if we look at this assignment, x and y are relevant for the theory of the reals, and on the other hand, x equal y is relevant to the theory of equality. And in this manner, the notion of relevance defines the subdivision of labor between the theories, among the theories. So the theory of the reals can make x and y equal or different by assigning explicit values to them. On the other hand, the theory of equality is responsible for deciding the truth value of the equality x equal y. We have theory modules so far for propositional logic, for linear rational arithmetic, for equality, and for arrays. And we also have a theory module for any stably infinite theory, for which we have a satisfiability procedure, simply because we define the single inference of this theory module as a coarse-grained invocation to the black box satisfiability procedure that detects unsatisfiability of a bunch of assignments, of a bunch of Boolean assignments to literals in that theory. Okay. Now, on the trail of CDSAT, what are we going to have? A trail is, as always in this kind of procedures, an ordered sequence of assignments. In CDSAT, we have two kinds of assignments, either decisions with the usual meaning as in CDCL, SMT, etc., or justified assignments. Justified assignments are those assignments that have a justification. What is a justification? It is a set of assignments that appear before in the trail, so the trail is ordered. So a justification of A is a bunch of assignments J that appears before A in the trail, and for which there is an inference in some theory module IK that infers A from J. Now, having an inference actually is not the only way to have a justification. This is really an example. This is going to be the case when L is Boolean. But also a non-Boolean L can have a justification, as in the example we saw before. In this case, when we get y gets 2 from x gets 1 and x plus y gets 3, these two are the justification for this. And this is not an inference. On the other hand, in most cases, the justified assignments are Boolean assignments, and then they are justified by an inference. Okay. Now, every assignment has a level, as usual. The level of a decision is defined as in CDCL, so every new decision opens a new level. The level of a justified assignment is the level of its justification, and the level of a justification is the maximum among those of its elements. This is also pretty standard. Now, with the CDSAT inference system, we have search rules and conflict resolution rules. And we assume a finite global basis, where global means that it is global for all the theories. So it is not that every theory has its own little basis. There is one global finite basis for all the theories, from which the theories draw values. And so the finiteness of these global bases to make assignments to terms is what we use to prove termination. Now, the search rules apply to the trail. We have a decide rule, as usual, which decides an assignment. It has to be acceptable and for a relevant term. We have a deduce rule, which adds a Boolean L if there is an inference from a justification that already appears on the trail. When does it come? So the procedure, as usual with this kind of procedures, goes on doing decisions and deductions. Deduction is the more general name we use in place of propagations, until a conflict arises. So what is a conflict? A conflict is a situation where from some J, which is a subset of the trail, we can infer an L, a Boolean L, but its complement is already on the trail. Then J, the premises of the inference, plus the complement of what is inferred form the conflict. Now, when a conflict arises, there are two rules. The fail rule declares unsatisfiability if the conflict is at level 0. The conflict solve rule solves the conflict or attempts to solve a conflict of level greater than 0 by calling the conflict resolution rules. There are 4 conflict resolution rules in CDSAT. 2 are backjumping rules and 2 are unfolding rules that explain the conflict by unfolding the conflict by replacing an element of the conflict with some other assignments. So let's see first the backjumping rules. They apply to both the trail and the conflict, and the backjumping rule apply in this situation. They apply when the conflict contains an assignment A, which is outstanding with respect to the rest of the conflict, in the sense that its level n is greater than that of the rest of the conflict. So it's greater than any of the other levels that appear in the conflict. And then there are 2 possibilities. One applies when this outstanding assignment is a first-order decision, and the other applies when this outstanding assignment is a Boolean assignment. So if A is a first-order decision, the undo rule will remove A and all assignments of level greater or equal than n. So in practice, we backjump to n minus 1. The backjump rule applies when the outstanding assignment is a Boolean assignment, and what it does, it backjumps to the level of the rest of the conflict and flips L. So it adds its negation with justification E. Why? Because if we have a conflict E union L, where this L is the outstanding assignment in the sense that its level is greater than all the other levels that appear in here, then if E union L is unsatisfiable, then of course, if from E union L we can infer an inconsistency, then of course from E we can infer not L. And this is precisely what a backjump does, putting not L on the trail. Example. Assume that we have our initial set in the combination of the theory of arrays, rational arithmetic, like this. Say that the procedure guesses that U and V are equal, giving to both some value C. And then it also assigns this value to the select store term, and then it assigns 0 to W, and then it assigns 0 also to the F select store term, and then it assigns -2 to FU. This is just a bunch of decisions that the procedure goes off into making. At this point, it can make 2 inferences in the theory of equality. It can infer that U is equal to select store. Why? Because F select store, no. This one it gets it because, let's see, because we gave to U C and we also gave it to select store. Okay, so from this decision and this decision we get this equality. And then because FU is -2 and F select store is 0, we can deduce that they are different. At this point we have a conflict because these 2 terms are equal, but the function f applied to them yields 2 terms that are different. So these 2 give a contradiction in the theory of equality. Now, the conflict applies to this term, which is the one of greatest level in the conflict. It flips it, and it clears the trail, saving this other deduction with this justification that is these decisions. And so this is an example of backjump. But we also have 2 other rules to deal with conflicts that are the explanation or unfolding rules. Now, for these rules, the idea is that we have the conflict, which is a bunch of assignments that cannot be all together. So we unfold the conflict by replacing an assignment in the conflict with its justification. Now, the crux here is whether the justification that we bring in contains a first-order assignment of the same level of the rest of the conflict or not. Of the same level of the, D is the whole conflict. So we replace some A in E with H. The point is whether the justification we bring in contains a first-order assignment of the same level as E or not. If it does, we apply resolve. Sorry, if it does not, we apply resolve. If it does, we apply undo decide. And what do these 2 rules do? Resolve does just this. So it replaces the justification of, it replaces A with its justification H. The proviso that H does not contain first order assignment is to avoid a loop. A loop which cannot happen with purely Boolean decisions, but can happen with first order decisions. Why? Because assume that we do not have this caveat. Then we could do a resolve and replace A with H. Then we would apply undo, they would undo the first order decision, say A prime, included in H. But then we could decide it again. Decide again A prime. And we can deduce again the consequence A of H. And then we would be in a loop. Why is this intuitively? In the Boolean case, this does not happen because when you undo an A, you put not A on the trail, and this prevents you from looping. But when you put on the trail x gets 3, and then you undo it, x gets 3 does not have a complement, because its complement are all the other infinitely many values for x, so it is not something that you can handle. There is no flip of a first order assignment. And so we can do this resolve only if it doesn't bring in an outstanding, a topmost first order decision that can cause us this looping problem. Now, what if the justification H contains such an outstanding first order assignment? Then we do undo decide. And we prove that this situation happens only if there are two Boolean assignments, L and F, in the conflict, both depending from this first order assignment A. And then what undo decide does, it flips arbitrarily one of these two. Because they are Boolean and they have a flip, we can get out of this situation and go to a different state, having not L rather than L. Let's continue with the example and let's see resolve at work. Let's see this job of unfolding the conflict. If you recall, we had this set and we were left with the initial decisions that we didn't undo. We had this deduction that also we did not undo with the latest back jump. And then from these we can restart deducing, and from U equals select store we can deduce this equality, FU is equal to F select store. And then we can also deduce FU equal W, because FU is equal to F select store and F select store is equal to W. So by transitivity from these two, we get FU equal W. And also by transitivity, we can also get this, because FU is equal to W and FU is equal to W minus 2. So we get W minus 2 equal W, which is of course contradictory in linear arithmetic. So at this point, resolve kicks in and it says, okay, what is the justification for this guy W minus 2 equal W, which is the outstanding one, the highest level? It is because of these two, FU equal W and FU equal W minus 2. So it replaces these by these two. Then what is the reason, what is the justification for FU equal W? We simply unfold the deduction steps we did before. This comes from FU equal F select store and F select store equal W. So now this is the conflict we have. And finally, where does this come from? It comes from U equal select store. So we unfold again and we are left with this. At this point, we don't unfold anymore. This comes from the input, this comes from the input, and this is the deduction that we did before. And
question.
yes.
Where does, in the first resolve, where does FU equals W minus 2 come from?
Input.
Oh, sorry, I didn't see.
Okay. So continuing, what happens now we back jump, because this U equals select store that we were left with is a topmost assignment that it is Boolean, so we can back jump, we flip it, so it becomes negated. And we jump back to level 0 because this thing belongs to level 0. Since its justification, if you go back, this thing actually came from level 0 because it comes from this decision and from this other decision. Okay. And then we are left, we assume that we decide again these, so we are back to level 0, we undo everything, we do again these decisions. Now, because we have learned this fact, when it comes to select store, we have to give it a different value, which is not the same as the one given to you. But at this point, with this assignment, we see that select store is different from V, because they get different value. And now we have a contradiction with I equal J in the theory of arrays, because I and J are the same index. So if we store value V in I and then we read it, we should get the same value V, and instead this assignment tells us it is different. And so we get a contradiction in the theory of array. This conflict leads to another big jump where we flip the culprit, this equality. Now it becomes positive. But now we have a conflict at level 0, because now we have U equal V, U different from select that we had learned back then, V equal to select store that we just learned, and these are incompatible simply by the theory of equality, because U is equal V, and this same term is equal to V and is different from U. And so the fail rule returns that P is unsatisfiable. We have three main theorems that prove the soundness, determination, and the completeness of CDSAT. So if CDSAT return is unsatisfiable, indeed there is no model for the input set. CDSAT is guaranteed to terminate, so every CDSAT derivation is guaranteed to terminate provided the global basis is finite. Completeness, if CDSAT terminates without returning unsatisfiable, then there is a model that endorses the final assignment we are left with on the tray. Last, satisfiability module assignment. This whole framework where assignments are the basic data, assignments and not formulae are first-class citizens, leads us to define a set of problems that we call satisfiability module assignment. So what is an SMA problem? It is the problem of deciding the T-satisfiability, so we are always modulo a theory, of course, of a quantifier-free formula, modulo an initial assignment of values to variables, whether Boolean or first order of any sort, doesn't matter, that comes with the input. So the input set now is no longer necessarily a bunch of formulae that we consider true to start with, our assumptions, but it may also contain specific assignments. In CDSAT, because it is so geared towards assignment and does not distinguish between Boolean and non-Boolean, can solve this kind of problems in a conflict-driven manner for a generic combination of theories T, provided, of course, they are disjoint, they have satisfiability procedures. Now, where does this kind of SMA problem come up with? Is it an artificial kind of problem? No. Actually, it comes up in enumeration of models. For example, if you want to enumerate model rather than just generating the first model, after you have the first model, you want to get a second one, then you're interested in giving as input to your procedure some assignments that exclude the model you already found. It comes up in parallelization because, for example, the cubes that we saw at work in the talk by Marin Hoyle are just conjunctions of literals that we start out with, and so they can be seen as an input assignment, Boolean in that case. And it also comes up in optimization. At the workshop at CADE in 2013, Leonardo De Moore and Grant Passmore had a proposal for an approach to optimization problems solved by iterative satisfiability problems. So you use iterative satisfiability procedure. In that case, it was the one for the algebraic reals, and you instrument it in such a way that every run, if it doesn't solve the problem, will generate some additional information in the form of assignment to variables that, if memorized, will exclude that path and allow us to converge towards an optimal solution in the limit. So satisfiability module assignment arises also in the context of reducing optimization problem to satisfiability problems, which is really a topic not very developed because I'm not aware of a continuation after that workshop paper, but I think it is quite interesting. And to conclude, this is the material we have. As I said, we have a paper at Nextcade, and we also have a technical report, which contains all the proofs and the details and support the conference paper. So thank you very much for being here and for your attention. Any questions or comments?
Yeah, you go first.
Just for the mouth. So this finiteness of this basis, I wondered about this. So does that work with the separate series? Don't they need infinitely many possible constants for the assignments? Like linear arithmetic will need all natural numbers there. But that sounds like an infinite basis, but maybe I misunderstand how it works.
No, we do not need infinitely many terms. If we had that, we couldn't guarantee termination. Basically, the answer to this variability can be found with finitely many ingredients. If you wish, it's an argument not unlike Hilbert theorem. You need finitely many instances to find the contradiction. So a finite basis is enough to prove completeness.
But you need to fix the finiteness beforehand.
Yes, and it depends on the input.
But isn't the fact that you can find instances of variability with finitely many constants dependent on the problem? Yeah.
That's not constants, it's actually finitely many
Terms.
atoms and terms and so on. So that,
Okay.
and these are basically derived from the ones in the input. Essentially, they're the terms that can arise
They're
in
terms,
any
okay.
proof
Right.
of contradiction
Right.
from the input.
Okay. So in reality, you can see the basis as the closure of what your inferences can generate. So this is how we show it.
But the disclosure is always finite for what you're looking at, or it's an assumption. Oh, it's an assumption. No?
Depends on the theory.
No, but like
On the theories.
for linear arithmetic, even for reals, it's finite. At least like now, or which is in.
Okay,
in some sense
let's take this offline and
Yeah, for
explain
linear
to me
arithmetic,
later.
it's the terms that can arise in a Fourier ones can prove, for instance.
Yes. So assignments can be arbitrary, yes, but during the procedure you arrive only with finite number of conflicts, and all these conflicts can be expressed as like Fourier modes from elimination, or even in non-linear it will be like staccato or whatever. Yes, but it's only a finite number of conflicts you can arrive to. Therefore, termination works even with arbitrary assignments.
So I guess the question again is, so the basis is determined by the theory, not by the input. The existence of a finite base, I should say, is determined by the theory, not by the input.
The actual finite basis.
The actual finite basis, but the existence of a finite one. And you guarantee that
for the
you're always
theory.
going to stay within that finite base in the algorithm. Is that correct?
Yeah.
And so examples would be, for instance, what he said, for real with for other theories, have you identified the finite basis?
Yeah, in the paper, all the theory in the paper.
How would you need to extend your example so that you have to use undo the side?
The example with undo decide is in the paper. I didn't put it in the slide because I thought it would go over time.
That's fair enough. That's the question.
Let me mediate a bit. I
Please.
think Jasmine had her hand first.
Oh, yes. So I had a more practical question. So if I understand correctly, like the context for all of this is you look at the existing SMT solvers today, and they probably do too much work in the theories, or the theories don't propagate enough information, and then you want to have richer information from the theories and possibly do a better next generation of SMT solvers. Is that the background, or am I misunderstanding the whole?
The whole point here is that, okay, the standard framework for most contemporary SMT solver is the DP and LT procedure that you find in the JACM 2006 paper by Cesare, Albert, and Roberto. And there you have a CDCL subsolver, which is like the central procedure, the king, and then you have a bunch of theories that are like satellites or satellite procedure, and they interact with the central solver by detecting conflict in the theory. So the solver goes on and builds the model, and the theory say, hold, there's a conflict in my theory, and it provides a lemma. Or else by generating lemmas indeed in the theory. So the theory procedure sees that there is a bunch of items on the trail and say, look, from these items we can get this other effect. Okay. Now, the problem is that in later years, people came up with procedures for example, all those fragments of arithmetic that lift CDCL to theory reasoning. So there is conflict-driven reasoning not only in propositional logic, as in the DPLLT framework, but in the theory itself.
And they want to do it for efficiency reasons. I
Exactly.
presume. Yeah.
For example, the NLSAT procedure, at least for the purely existential fragment, is reputed as being more efficient than cylindrical algebraic decomposition, precisely because rather than enumerating possibilities, it gets only the possibilities that are needed in a conflict-driven manner. So then the question was, how can we integrate these new kind of procedures, inherently conflict-driven at the theory level, into more general framework? So MCSAT did the interaction between one such procedure and CDCL, the subsolver.
Right.
CDSAT does it for multiple such procedures, all conflict-driven, and it brings the whole conflict reasoning at the central level altogether in a combined manner.
So yes, so in practice it does mean that you could build an SMD solver and it might be able to beat CVC4 at the competition or something like that, right?
Let me
add to that. Let me add to that. I mean, the advance in MCSAT and is basically that. I mean, in the DPLLT style, you can only generate theory lemmas in the input language, okay, in input literals.
I have to correct you, that's not quite true, but that's not really the difference. The difference is you sign. You can generate.
The lemmas, I mean, it's assumed that you
Lemmas,
find a theory
so
conflict
there is an
and then input.
extension of DPLL where you can generate.
Yeah, but these procedures, the MCSAT style procedures, can generate theory lemmas in some new, with new terms, new literals in them.
Sorry,
So
I have to insist. DPLLT there's an extension called putting on demand.
No,
Yes,
you're
we know
not
that
correcting me.
extension,
You're not
Chief,
correcting me. You're just.
But all it does,
Fine-tuning.
it introduces proxy variables for the equalities generated by equality sharing.
Yeah, that's the other point. So giving the assignment is a more compact way of actually guessing an arrangement. If you guess the arrangement between n variables, it can be quadratic in size. But if you just say, x gets 1, y gets 2, you already said x is not equal to y in an implicit way. And so the advantage of these procedures is that in that phase, there's propagation and there's guessing. There's no inference going on. It's only when you hit a conflict, means you're so lazy about it. It's only when you hit a conflict that you actually do any inference. So so we expect these procedures to be more efficient. Yeah. Wait, actually, Arnold had a question first. I have him on the queue.
So how powerful is this, or how powerful do you expect it to be? Are there problems that you can solve that couldn't be solved before, and that would have been solved before in a much slower way?
Well, in terms of implementation, this is still to be seen. As of now, there is still no implementation of CDSAT. Stefan has the prototype, but we haven't deployed it yet. And as for MCSAT, there are 2 implementations that I know of. One is in EIX2, one is in CVC4, but in both these systems, the MCSAT procedure is not really integrated at the center of the solver. It did not become the central philosophy of the solver because both solvers pre-existed and were based on the DPLLT philosophy. So they have MCSAT as a sort of an external option or another possibility, but it is not really a completely new design. So I think it will have to be seen when we will have a solver which is designed from scratch based on this philosophy and see how well it does.
Are you working on that?
We
Or is that
plan to,
someone
yes,
else?
yes. We need to do the journal paper
CDC5.
implementation.
Yeah. So, to add to that, actually, the architecture, when you put the SAT solver as the sun, as Maria Paola said, is that you actually get a pretty lousy architecture, which is a pain to implement. Okay. So so I gave a talk in I forget when with my collaborator Douglas Bruno, where we pointed out the flaws in the architecture and actually proposed this architecture where all the solvers are equal. But that was still a very abstract thing. This is a much more concrete realization of that egalitarian architecture where the SAT solver actually sits. And in the talk I gave, actually, the equality sharing was actually front and center. That's the thing that actually mediated between these. And that's, in some sense, what's going on out here. The equality sharing is actually the thing that mediates across theories. So if one theory doesn't know, what does 2 and 3 mean, just tell me x is not equal to y. So that's the level at which things operate. And in the case of this nonlinear thing, it is actually more efficient than the procedures that preceded it. MCSAT was actually more efficient. So this is something that's adopted by the many implementers now. But we don't know on this combination thing, we don't know anything yet. And also I should point out that implementation is where you squeeze out efficiencies. I mean, it takes a lot of skill to do the very clever implementation. So it takes many years to actually find all the implementation tricks.
So exactly what implementation of this exists already? I didn't get that.
No, we already have the
There's no
MCSAT,
implementation.
CDSAT.
This thing hasn't been implemented.
CDSAT no, MCSAT or NLSAT, yes.
In MCSAT, what implementation language issues this list?
No, there are different implementations. There's one in Z3, there's one in CDC4, there's one in YIX.
I have a naive question. I'm a user of interactive peer improver, so when we use an automatic tool, we like to have a proof, a certificate at the end. And does it change this? Is it easy to generate certificates or something like that?
Yes, this one can actually generate proofs, and that is current work. We are presently doing the proof generation part. I absolutely agree that it is necessary to generate proofs. So in the presentation I gave today, proof generation is not included, but it is current work.
Yeah, but I don't understand, what does it change? In the
Well,
generation compared to the DPL. I mean, DPLL, I understand roughly over what
well,
the proof
in
would
the
like.
PLLT, what you have is a proof by propositional resolution, which is basically what you get from CDCL. But when you are in the modular theory case, you also have the lemmas coming from the theories. So in order to have a complete proof, you also need the T-satisfiability procedures for the theory to provide you with subproofs that then will be plugged like subtrees into the resolution proof tree. Okay?
Yeah.
Here, it won't be too different. What we need, however, is just to keep track of the information of the inferences to generate. Basically, we will generate the proof by composition of the inferences that are done by the various theory modules. And so we are writing down these days this composition part. We need to decide whether to put it in the journal paper or in a separate paper. It's mostly a matter of a number of pages.
But it shouldn't be problematic, right? I mean,
No, it's not. But it is interesting because we
yeah,
do
sure,
want
sure.
to have proofs.
There's no
No, it's not
fundamental-
problematic at all, but it's interesting.
So you were quite explicit on the difference between inferences and deductions, right? Deductions got you a Boolean, and inferences got you just another kind of assignment. But in these proofs that you would generate, both also the justifications that are not deductions would have some deductive proof part coming from the theory?
No, not really. Maybe there is a little bit of misunderstanding. Sorry about that. We use deductions, and we use the name deduce for the rule as a generalization of what in CDCL is called propagation. Okay, and then we use inferences for the inferences that justify these deductions, but it's not really
Okay.
We could also probably name them otherwise. It's not such an essential
Okay.
thing.
It's a terminology.
So for example, transitivity of equality for EUF would be an inference, right?
Okay.
Rule and so
Right.
on.
Okay.
Okay, so we should,
Okay.
ask
So,
one last question. Then.
as far as the assumptions on the theories are concerned, so I seem to have gathered the following. So they have to be signature disjoint. Well, as far as the function symbol is concerned, they should share function symbols. Right?
Yes.
Are you assuming stable infiniteness or something stronger?
Am I
different?
assuming what?
Stable infiniteness or something different?
What we assume in the proof of completeness is that at least one of the theories has information about the cardinalities of the shared sorts, of all the shared sorts. So that stable infiniteness is a way to do that. Because if the theories are stably infinite, there is at least one theory that knows that all the sorts are interpreted with infinite domains.
Okay, so
But in principle, the information could also come from some other source, and in this manner we can accommodate also non-stably infinite combinations. For example, the theory of arrays with some finite domain.
So, concretely, what does that mean in this case? What,
Well, there would have to be one theory, say theory T1,
yeah,
which knows that the sort of the values that we put in the array is a finite sort, that there are only, say, 2 values or 3 values for this kind of arrays.
and,
There is one theory which knows this, because the way we structure the completeness proof is that first we prove a completeness property of this one theory, and then we prove the completeness of the other theories relative to this one. And in this manner, we manage to show that there is the model that endorses the assignment.
Yeah, but usually the problem is when the domain is not fixed, like you have only odd the size is odd numbers, yes, even. So it's not easy to communicate the size of
Oh,
the
yes.
relevant
this is an
relevant domain.
Well,
yes, so
the
it's
reasoning,
not,
the
size
explicit
is
reasoning
not-
about cardinalities is not in the current wares of these procedures, but in the proof of completeness, we have this assumption that generalizes the requirement of stable infiniteness for all. If they are all stably infinite, we just go that way. If one is not, we have this assumption that at least one theory knows the cardinality, and therefore in that theory we can build the model respecting those cardinality, and then the other need to be complete with respect to that one in such a way that the model with the needed shared cardinality can actually be built in the combination. We have a lemma for gluing the models together and respecting this kind of requirements.
have you identified ways, and this is my last question, have you identified ways to recognize that these conditions hold? Because, you know, they are fairly abstract. If I give you a theory, can you tell
Right.
me if you can plug it in or not?
There are, in the paper identifies
Yeah, what?
some sufficient conditions or something.
There are sufficient conditions?
Yeah, there are sufficient conditions, yes, that need to be checked manually, of course.
Yes, yes.
So, I just want to, these are all great questions, that's why, I thought we should get the discussion going. With regard to Lauren's question about interactive theorem proving, I think, there may be a style of doing these kinds of things interactively as well, where you kind of guide the search by proposing some values and then saying, finding a conflict. So I think some of these ideas might be compatible with interactive proving as well.
It'd be interesting because you're suggesting values instead of lemmas, right? It would be a very nice, different way to do that.
But even more than that, I think that this entire paradigm of conflict-driven reasoning or conflict-driven automated reasoning is very suitable for interaction, for integration with interactive theorem proving. Precisely because a very central concept in conflict-driven reasoning is this notion of explanation, of doing inferences only to explain conflict in the automated tool. And then this explanation is something that one could envision is something that could be relevant also to the interactive proof, to the interaction between the human user and the engine. So this explanation could, right now they are kind of low-level, bit-level thing kind that the prover deals with, but in the future we can envision more general sorts of explanations that are interesting for humans and not only for provers, and that could be brought up to the level of the human-machine interaction. But this is all future speculation.
Okay, one very last thing. You proved silence, completeness, and delineation. Would it be reasonably easy to formalize those proofs? I mean, you formalized, what was it, Shostak a couple of times, right? So
These are not at all hard to
not
find.
at all. Someone should do it.
So yeah, these are all like, 6 to 10 week projects. That,
So if I have a master's student,
Undergraduate,
I
master,
say, here I have a
those
nice
kind of-
project.
You could do it yourself.
No, I have to ask.
No, actually, I find the students are a lot better at it than I am. So they're very good at this. But, yeah. Okay, thanks.